Alright, this is Newton's second law in complex situations, lesson 3.3b for physics 20. So, first thing, what is Newton's second law? Well, Newton's second law is simply put F equals ma. Now, again, on your formula sheet, we see that as A is equal to F over M, but with that, either way is fine, it's just that. But we're going to take a look at situations that require more than just using this formula. Now, let's start off with an example of what we mean by that. An elevator with a mass of 900 kilograms is accelerating downwards at a rate of 1.3 meters per second. What is the tension in the cable? Well, remember that net force is actually a combination of these two forces. So there's two forces, gravity and tension. And we can picture it just kind of like that, where this is Fg, and we'll call this Ft. Right, now, because it's accelerating downwards, the net force, mass times acceleration, is equal to the force of gravity, mass times acceleration, plus the tension, and that is what we're looking for. So we put 900 times negative 1.30, and that's because it's accelerating downwards. It's going to be equal to 900 times negative 9.81 plus the tension. Right? Well, evaluating that, that's negative 1,160 newtons, which is equal to negative 8,820 newtons plus tension, which, moving this over, you're adding it, which gets you a tension of 7,659 newtons. And it makes sense that if this is accelerating downwards, that gravity would be bigger than the tension. Okay, now the key thing with all of these is, first of all, use your free body diagrams, right? That will help us find the net force acting on the object. If there's multiple items, they can be considered individually as well as together, and you can flip back and forth between them. But the question then becomes what mass, but really it's just whatever mass you're taking into consideration. So to find the overall force or acceleration, use the total mass of all the objects. If it's for part of a system, well, use the mass for just that part of the system. Let's take a look at another example here. Two blocks in the above diagram, they're being pulled by 19.2 newtons, and we've got friction coming from both these blocks this way for a total of 15.8 newtons. We want to know what the acceleration of the blocks are, but we can consider this as one block. One big massive block with 14.3 plus 12.2 gets you 26.5 kilograms with a force of 15.8 newtons this way and 19.2 newtons this way. We're using those combined masses. But we've got two forces acting on the object, and so the net force comes from taking that positive 19.2 newtons, and we're adding that to negative 15.8 newtons because that is going in the opposite direction, which gets you a net force of 3.4 newtons. So now that we have the net force and the mass, we can find the acceleration of those masses. Acceleration just being force divided by mass, which would be 3.4 divided by 26.5, or the acceleration being 0.128 meters per second squared. Right? Now in the diagram, that's to the left. You may want to put left in there, but we're not specifically told a direction, and so really if we left out 0.128, that would be fine. The next one though is a little bit interesting. Is what is the tension on the string between the blocks? Meaning this tension right here. Well, first thing we're going to do is figure out how much of the friction is actually happening with just one of the blocks. And we could really do either one, but we're going to actually use the 12.2 block. And the reason for that is because it'll have less forces acting on it. It'll have tension and force of friction, as opposed to this pull, tension, and force of friction. Less forces by dealing with this block. So it's going to be easier for us to use that block. So taking the 12.2, finding the friction, well, the friction we know is 15.8 newtons, and we're just going to multiply that by 12.2 over 26.5. And that will get us a percentage of this mass that is of the 15.8 newtons, what percentage is responsible from this particular mass. And that calculates to 7.27 newtons of friction acting on just this block. So if we were to draw a diagram of this block, we know it's 12.2 kilograms, and it's got a force of friction acting at 7.27 newtons, and what we've got here is the tension in the rope. We also know from part A here that it is accelerating at 0.128 meters per second to the left. So it's got an acceleration of 0.128 meters per second that way. So from here, we can figure out what is the net force acting upon this object. And then we can use that to find the tension as the sum of those two forces. So let's find that net force, which is just equal to MA, which is 12.2 multiplied by 0.128. So that gets you a value of 1.565 newtons. So that's the net force. That is the tension and the friction coming together. Now the tension is going to be greater than the friction because it is accelerating to the left. So we can also say that that 1.565 is equal to the tension and the force of friction. 1.565 is equal to the tension plus negative 7.27, which means in total you get 8.84 newtons as the tension. And that is the tension between blocks. Again, when we had finding overall acceleration of a system, we used the total mass, the 26.5. But here we were looking at just part of a system, so we used the mass of 12.2. In an Atwood machine, we've got two masses that are sliding together, and so this is going to be falling, and because this has a force, it's going to come around this way but be held up by this force that's moving this way, right? And so this 1.2 kilograms is going to slow down the 1.8. Well, we can find the net force acting on either of them, or the force of gravity, I should say, acting on either of them, and that's just going to be MA. MA, where acceleration of gravity. So 1.8 multiplied by 9.81 means that this is moving at 17.66 newtons down. This one here is 1.2 times 9.81, and so this has a force of 11.77 newtons. And again, down. But yeah, they're both down, but in the same way, they're both acting against each other in terms of the way this pulley is keeping them. And so if we take a look at, well, what is the net force acting upon the object? Well, that's going to be 17.66, which we'll call positive. And we're going to add to that 11.77 because it's going really in the opposite direction. We'll call that negative. So you have a net force of 5.886 newtons. Well, to find the acceleration, we've got the net force, and the total mass here is 3. So to find the acceleration, it's just force divided by mass, or 5.886 divided by 3. That gets you an acceleration of 1.962 newtons. Well, if you want to find the tension of the string, you're going to zero in on one of them. Now, it doesn't matter which one you zero in on, because they're both going to have two forces. Either you're going to have it with the gravity being greater than the tension, or the gravity being less than the tension. So let's just choose one. We're going to choose this one just really because. And so we've got a 1.8 kilogram mass with a force of gravity going down at 17.66 and a tension. We know that its acceleration is 1.962 newtons downwards. Alright, so from here we can find out what that net force is. 1.8 times 1.962, that's 3.53 newtons. And that's a combination of these two, so we can say that 3.53 newtons is equal to the tension and that force of gravity, which is going 17.66. Now, because we've called this net force down, we should put negatives on those. And adding the 17.66 to both sides gets you an answer of 14.1 newtons as the tension. And that will have the opposite sign of the 3.53 and the 17.66. Okay, another teacher's got a little helpful video that we'll go through right now.
Okay, for this one I'll tell you about Atwood's machine problems. First let me tell you what they are. An Atwood's machine problem is when you have a pulley and there's two masses, and say this mass is heavier than this one, this will go down if they're attached to a string. The string attaches them to each other and it's looped over a pulley, and the pulley might be fastened to the ceiling. So when this one goes down, this one goes up. A guy by the name of Atwood used this type of machine to study acceleration of objects. That's why they're called Atwood's machines. With this one, this is a similar system, except for now this is on a table. Might be a frictionless table, or maybe a table that has friction. But then a string goes over a pulley and is attached to this M2. So when M2 descends, M1 goes across the table. You probably did a couple labs on these things last year. Okay, for this unit, for unit C, we're going to assume that the string has no mass. No mass. Or in other words, it's a light string, so it's not going to affect the masses of the system. We're also going to assume that the pulley has very little mass. We say the mass of the pulley is negligible. We'll also assume that there's no friction in the pulley's axle. Those are all assumptions that make the system much more simple to study at first. We can add in the complications later. All right, let's get started. For the Atwood's machine that is in this position, if this is M1 and this is M2, and if you can assume that this is attached to the ceiling. I'm not always going to draw the ceiling when I do these, but it's attached to a ceiling. Let's say that M2 is heavier than, it's greater than M1. So it's going to accelerate this way. And let's say we want to know two things. We would like to know the acceleration of M2, and we would like to know the tension in this string. Okay, well, the magnitude of the acceleration of m2 is the same for this one and this one. They both have the same magnitude of acceleration, even though this one goes up and this one comes down. That's because they're attached to a string. They're attached by a string. So if this is going 2 meters per second squared down, that's got to be going 2 meters per second squared up. What we are going to do is we are going to put some forces in here. This is m2g down this way. And I didn't leave myself much space here. But it's, I'm going to draw this, make this is a big force. And this is a smaller force. This is going to be m1g down. So m2g down on this side and m1g on that side. What we'll do is we'll straighten these out. I know they're pulling in two different directions. They're both pulling down, but isn't that kind of like this? Isn't it like a system, if we straighten this out, of m2g pulling this way and m1g pulling that way? And isn't this the same thing that is just one big system of m1 plus m2 being pulled with these two forces? So the acceleration of this system is going to be m2g minus m1g all over m1 plus m2. Okay, let's put some numbers in so I can show you what I'm talking about. Pulley, 2 kilograms, 3 kilograms, okay, what will be the acceleration of this system? Well, that's kind of like a 2 kilogram being pulled with 20 newtons and a 3 kilogram being pulled with 30 newtons. And so the acceleration is equal to the net force, that would be 10 newtons since they're pulling in opposite directions, divided by the mass, which is 5 kilograms. So that's 2 meters per second squared. Okay, now you might ask, well, how do you get the tension? How do you get the tension in the rope? Well, let me show you what you do. You tunnel vision on just one of these. If you just tunnel vision on just one of these, then let's look at what's happening there. I'll draw this down here so it's less confusing. We have that 3 kilogram mass. We have 30 newtons down. And you know what's pulling up on it? Not this guy, it's the rope. The rope is pulling up with a tension Ft. Guess which one's bigger, the 30 or the Ft? I kind of gave you a hint. You know why it's bigger? The 30 is bigger? It's because it's accelerating down. The 30 must be bigger. Now I just apply Newton's second law. A equals F net over m. So A is 2 meters per second squared. I already know that. So I'm going to put in 2 meters per second squared. Yeah, I had to do that before I could do this. The net force, 30 is winning, so I'm going to say 30 newtons minus Ft all over the mass. Now, that's my system. The dotted line is my system, so that's 3 kilograms. Solving for Ft, let's see, that's 6 newtons. So that would have to be 24. Ft is 24 newtons. See how that works? I could have used the 2 kilogram one. I would have gotten the same thing. Can I see if I can fit that over here? The 2 kilogram one has 20 newtons down on it. That's 20 newtons down. And Ft is up on that one as well. But in this case, the Ft is winning because this one's accelerating up. So I would say 2 meters per second squared. That's the acceleration. is equal to the net force. That would be Ft minus 20. The Ft is winning for this guy, all over 2 kilograms. 2 kilograms, because I'm looking at the 2. When I solve for that, lo and behold, I get 24 newtons. The tension in a string is the same throughout. Okay, I think I'm going to need a part 2 to show you the Atwood's machine for this type of a system. So I'll see you in a little bit.
Okay, so let's take a look at another problem here. In this one, we've got a 40 kilogram weight on a table. So this is 20 kilograms, and this one is also 20 kilograms. However, we've got a force of friction, and I did change it here. Coefficient of friction being 0.2, which translates into a friction of 40 newtons this way. Well, the other force that's acting upon this system is this mass that's going down. And so that's F is equal to mass times the acceleration due to gravity, which is going to be 20 times 9.81. So that force is going to be 196.2 newtons. So the net force overall, we've got this force and this force. That net force, we're combining those two forces, is 196.2 plus negative 40, which gets you 156.2 newtons overall. The acceleration, F over m, is just going to be that 156.2 divided by 40 kilograms, because overall that's moving this 20 and this 20. So that acceleration is going to be 3.9 meters per second squared. Now that we've got the acceleration of the objects, we can zero in on one of them, and it doesn't matter which one, but let's choose this one here. And you've got two forces acting upon this, the 40 and some tension in the string. But M1 has a mass of 20 kilograms and is accelerating to the right 3.9 meters per second squared to the right, where that's the tension, and this is 40 newtons. The overall force is 20 times 3.9, and so 20 times 3.9 is going to be 78 newtons. So it's 78 newtons altogether, the tension and the force of friction. So we can also say that that is equal to the tension and the force of friction. So 78 is equal to the tension plus negative 40, because it's going the opposite direction of that acceleration, which means you get 118 newtons as being your tension. All right, there is another helpful video here.
Okay, we're back.
But we're going to skip it within this video. And I would like you just to try this one within a frictionless system. Give this one a try, pause the video, and see if you can get it, and then come back. Okay, because this is a frictionless system, we really only have one force acting upon these two masses, and that is the force of gravity from M2, which is 127.53 newtons, which is moving not just 13 kilograms, but a total of 20 kilograms, because this one is 7. And so net force divided by 20 gets you an acceleration of 6.4. Give yourself a round of applause if you, in fact, got that. And the second part here is, what is the tension in the string? Again, pause the video and then let's see if you get it. And so whether you chose M1 or M2 doesn't really matter, but choosing M1 means that you only have one force acting upon this object, which is the tension, which makes things really nice here because you've got a 7 kilogram mass accelerating 6.4 meters per second to the right. F equals ma gets you a 45 Newton net force or tension on the string. Hope that helps, and thanks for watching.